All right, today we're going to dive into a couple of puzzles in physics that just seem, well, impossible. They're the kind of problems that really mess with your intuition about how the world is supposed to work.
So first up, think about this. How do you take a picture of a single atom? I mean, we can get these incredible images of galaxies billions of light years away, but taking a snapshot of something right here, something so tiny, it's a whole other challenge. How on earth do you do that?
And then, for our second puzzle, we have the ultimate dream, right? Free energy. Imagine just slapping some magnets onto a train, lining the tracks with copper wire, and boom, limitless free electricity every time the train goes by. Sounds a little too good to be true, doesn't it?
Now, to figure these out, we're not going to be looking for some clever loophole in the laws of physics. Nope. Instead, we're going to see that the solution comes from understanding those very laws on a much deeper level. And the answers are, well, they're pretty amazing.
Okay, let's get right into it with our first puzzle, the invisible portrait. Why is taking a simple picture of an atom so mind-bendingly hard?
Well, it really just comes down to a problem of scale. You see, the way we see things is by having light waves bounce off them and into our eyes or a camera. But here's the thing, an atom is literally thousands of times smaller than the wavelength of visible light. The light waves are just too big. They can't even feel that the atom is there. And this is really the key. Instead of bouncing off the atom to make an image, the light waves just bend around it. It's called diffraction. You can think of it like trying to figure out the shape of a single grain of sand by watching ocean waves hit it. The waves are just going to roll right over it without telling you anything.
Okay, so you're probably thinking, well, that's an easy fix. If the waves are too big, just use smaller ones. And that's a great idea. Gamma rays, for instance, have wavelengths small enough to interact with an atom. So problem solved, right?
But there's always a catch, especially in physics. You see, a shorter wavelength means way more energy. So hitting an atom with a gamma ray isn't like shining a gentle light on it. It's more like hitting it with a tiny, superpowered cannonball. You'd either obliterate the atom or send it flying.
Honestly, this is the perfect way to describe it. Yeah, you'd know the balloon was there for a split second, but you're not going to get a picture of it. You're just going to get the aftermath. So that approach is a total dead end.
So if all forms of light are out, what's left? The solution comes from a totally different and, frankly, much weirder part of physics. The answer isn't a wave at all. It's a particle.
And this brings us to one of the wildest ideas in all of science, wave-particle duality. It turns out that tiny particles, like electrons, can also act like waves. And here's the really cool part. We can actually control their wavelength. How? By changing their speed. The faster we make them go, the smaller their wavelength gets.
And we use this bizarre quantum trick to build one of the most powerful tools we have, the electron microscope. It's brilliant. We take a bunch of electrons, speed them up like crazy until their wavelength is super short, and then we use magnets to focus them into a beam. We shoot that beam at our sample, and the way the electrons scatter or pass through creates a kind of shadow, an image on a detector.
So there you have it. By leaning into the weirdness of quantum mechanics, this idea that a particle can be a wave, we can do what light could never do. We can actually take a picture of an atom. And with that, puzzle number 1 is solved.
All right, now for our second puzzle, that tempting idea of getting something for absolutely nothing. Is it really possible to get free electricity from a moving train?
Now, this whole idea starts with a totally legitimate piece of physics known as Faraday's law. It's simple. Move a magnet through a coil of wire and you generate electricity. So the plan seems solid. Magnets on the train, coils on the track. As the train moves, you should get free power.
But hold on a second. There's this super important, unbreakable rule in the universe, the law of conservation of energy. You can't just create energy out of thin air. You can only change it from one form to another. So if we're creating all this electrical energy, where is it coming from?
Well, the hidden catch is another law, called Lenz's law. And it's basically nature's fine print. It says that the electric current you create, well, it generates its own magnetic field. And that new field always pushes back against the magnet that created it in the first place.
So let's look at what's really happening. The dream is free power. But the reality? As the train's magnet moves into the wire loop, the loop creates a magnetic field that repels it, pushing back. Then, as the magnet leaves, the loop's field flips and tries to pull it back in. The end result is a constant braking force, slowing the train down.
So you see, the electricity isn't free at all. You're actually just converting the train's energy of motion, its kinetic energy, into electrical energy. And to fight against that constant magnetic drag, the train's engine has to burn more fuel.
You're just paying for the energy in a different way.
So, we've got these two puzzles that seem worlds apart, right? One's about the quantum realm, the other's about classical mechanics. But what do they really have in common?
Well, in both cases, the answer wasn't about finding a clever trick or a loophole. The solution came from understanding the rules of the universe more deeply. It's not about trying to cheat physics, it's about actually knowing how physics works.
So what are the big takeaways here? First, down in the quantum world, things get weird, and particles can act like waves, a fact we can actually use to our advantage. And second, up here in our world, there's no such thing as a free lunch. Energy is always, always conserved.
And all of this kind of leaves you with a final thought, doesn't it? These fundamental laws often lead to answers that seem completely counterintuitive. It really makes you wonder, what other common sense ideas that we hold are just waiting to be completely overturned by a deeper understanding of how our universe actually works? Thanks for joining me.